We have been discussing probability distribution for discrete random variable, which assumes a countable number of distinct values such as the number of family members, the number of consumer visiting a drive-thru, the number of leakage in a pipe. Now we will continue our discussion with the other type of random variable, the probability distribution for continuous random variable. A continuous random variable is characterized by uncountable values because it can take on any value within an interval. Example of a continuous random variable include the investment return on a mutual fund, the waiting time on a toll booth, and the volume of soda in a cup. We will focus on the normal probability distribution, which is the most extensively used continuous probability distribution. However, before we go on discussing normal probability distribution, we'll start first in understanding the concept of continuous distribution and start with the first type of continuous probability distribution, that is the uniform distribution. Recall that a discrete probability distribution is a probability distribution from a discrete random variable. Thus, a continuous probability distribution is the probability distribution from a continuous random variable. If discrete random variable x assumes a countable number of values, a continuous random variable is characterized by infinitely uncountable values where the values can take any values within an interval. So if you draw a number line, a continuous variable may take values between a discrete value. As a result, when we compare the probability distribution of discrete and continuous probability distribution, a discrete probability distribution will look like a bar chart, and a continuous probability distribution will have a smooth continuous curve. For discrete random variable, we can compute the probability that it assumes a particular value x, or written as px equal to x. For instance, for a binomial random variable, we can calculate the probability of exactly one success in n trial to be px equals to 1. We cannot make this calculation with continuous random variable. The probability that a continuous random variable assume a particular value x is equal to 0. Thus, for a continuous random variable, it is only meaningful to calculate the probability that the value of the random variable falls within some specified interval. Therefore, for a continuous random variable, the probability of x is between greater than or equal to a or smaller than or equal to b is just equal to the probability of x greater than a smaller than b equal to x greater than or equal to a smaller than b, or x greater than a smaller than or equal to b, because the probability of x equal to a and x equal to b are both 0. So the probability of a continuous random variable is stated in this way. For a discrete random variable, we have a probability mass function which shows a list of the values of each discrete random variable x with the associated probabilities. For a continuous random variable, the function is called the probability density function, denoted by fx. And this is the example of how a probability density function curve is. The probability that the variable assume a value within an interval, let's say the probability of x between a and b, is defined as the area under the fx. So let's say that this is fx between points a and b. Moreover, the entire area under fx over all values of x here must equal to 1. This is equivalent to the fact that for a discrete random variables, the probabilities add up to 1. As in the case for a discrete random variable, we can use the cumulative distribution function denoted by fx. This is for cumulative distribution function. And we use cumulative distribution function to compute probability for a continuous random variable. Let's say that fx equals to the probability of x less than a value. So this denotes the area under the probability density function, or we can write it, for example, the probability that x is below a. So this probability is denoted by this area. So all values build up to a. In other words, we interpret the probability that x is smaller than a is just the probability, the value of the probability is the area here under this curve up to a.